So I want to show you guys an example kind of to motivate what we're doing. So here is, well, let me take, here's a program that that I wrote for my other class, okay? And this language looks like complete, might as well be in Greek to you guys, but this is what assembly, okay, looks like. So it's below a high-level language like C. Okay, so for sake of demonstration, let me close a bunch of these things. Okay, let me write just a very simple program, or okay, that's going to do basically very little. Okay. Okay, so and now of course I have to save this. Oops. Okay, so I'll just call it whatever C file. Okay, so this looks, relatively similar to the kind of Python or just writing code on by hand. I've done it in C here for technical reasons, but basically what all does this program do? I declare two numbers, A and B, and assign them the values 3 and 5, which I just pulled out of thin air. And then I declared the variable C to be the sum of the two, okay? And then I printed it, the sum. Okay, nothing at all exciting. Okay, so my question then is, oh, sorry, I forgot one instruction which you guys can ignore. Okay, so how many instructions are there here? Yeah. Instructions. Okay, I guess what do we mean by an instruction? Right? Is line 7 an instruction? Yes. Is line 8 an instruction? Is line 9 an instruction? You might even argue it's 2. Okay? Because I'm declaring the existence of a variable and I'm also assigning the value to be whatever. Okay? This print instruction, well, that looks like a single instruction, but printing, might take more work. And then this thing at the bottom, return 0, you guys can ignore. Okay, so great. So let me take that thing, okay, and all right, what was it? Oh, because it's a C file, duh. Okay, so what I just did was compiled it basically to take it from code into something that could actually be executed. And if I run it, well, then, okay, it prints out 8 to the console, big shock, okay? But this first command that I did, okay, took C, okay, so my high-level language, and it produced assembly, which is one step sort of lower, okay? What's the lowest step that you can get with programming a computer? Well, all the ones and zeros, right? and obviously, if I just put a bunch of ones and zeros up on the screen and said, "Hey, here's a program," you guys would look at it and be like, "Okay, great, yeah." You wouldn't be able to read it at all. Okay, um, something like Python or C is, I mean, I think we would argue that this is very human readable. Okay, yeah, there's some technical bits there, and you got to be careful with this. In C is very picky about syntax, so the semicolons there at the end of each instruction, I have to be very careful to make sure not to forget them, and lots of other things. But you know, this is basically human readable. Okay, all right. So the we've got human readable stuff, human unreadable stuff at the very bottom, which would be all the ones and zeros, right? The actual like binary, okay? And then there's this layer in between, which we call assembly. And this is what the assembly code is, or machine produced assembly code, okay, for the exact same program that I just wrote in C. Okay, now, is this human readable? Well, okay, maybe it's not readable by you guys because you don't know what any of these instructions mean, okay? But if you did know what all of those instructions individually meant, then you could kind of think through what all of these things are doing, okay? Um, you guys buy that, right? Okay, so this is maybe not human readable to you, but it is human readable to me. Okay, and the guys that are in, you know, the CS majors that are in or have taken CS241, where we program in this language directly all day long. Okay, okay, so great. The okay, but like I said, this is the exact program that we just looked at in C. You know, the thing that just printed the number 8, no big deal. Okay, so when we said in C, it looks like it was what, 4 instructions, maybe 5 if we wanted to kind of be picky, is actually a whole lot more of these things. Okay, and in particular, you know where the addition's happening that added the 3 numbers to, or the 2 numbers together to get 8, right there, line 26. Okay. Um, okay, and where did 3 and 5 come in? Well, look right there. There's 3, there's 5. Okay. And yeah, okay. So last time we talked about this sort of toy processor, okay, this toy architecture that one of the authors of the sort of the formerly required book devised basically just for teaching purposes. Uh, and okay, so how does this thing work, or how does any processor work? Okay, or not any processor, but most of them. Okay, most processors are what we would call a load store thing. Okay, so if I want to add 2 numbers that are stored out in memory somewhere, I have to first copy them from memory into uh, a sort of temporary a temporary memory cell inside the processor, and that thing is called a register. Okay, some processors have very few of these things. Our made-up processor has 16 of them, which is a lot. The ARM architecture, which is what powers the chip that's in the Raspberry Pi, and also basically every cell phone that's in this room, and every iPad or tablet that's in this room, um, and anybody have an Apple Watch on? Yeah. Let's see what else. Anybody have an Apple TV? No, or a HomePod or any of those gadgets? Okay, so they're all running ARM architecture processors, and the 64-bit ARM ones have 32 of these registers. Okay, so you need these things to do, you know, sort of they're like literally what's in front of your eyes right now as you're manipulating data. Okay, so right now this obviously doesn't look very human readable to you guys. Okay, for two reasons. One, it's for an architecture you don't know, and two, you don't know what the instructions mean anyway. Okay, so let's go to back to the notes that I downloaded, and let's see where I put them. I think it's here. See if we have anybody online today. Oh, 3 people. Okay, so let me blow this up a little bit. Okay, so here's the details about what we have on this processor, okay? So 16 registers, and they're addressed 0 through F. They're each capable of holding 8 bits worth of data, okay? So this is why, well, one reason why when we were doing two's complement and floating point and all of that stuff, we basically restricted ourselves to 8-bit numbers. Okay, this was one of the reasons that we just restricted to 8-bit numbers because this computer handles 8-bit numbers. The other reason was just simply for time and convenience because is working with 8-bit numbers any harder or easier than working with 32-bit numbers? Conceptually, they're identical, right? The only difference with 32-bit numbers is there's a lot more stuff to write down. Okay, but if you can do it for an 8-bit thing, you can do it for a 32-bit thing. It just takes longer. Okay, so that was the other reason. Okay, so we got 16 of these registers. We have 256 cells of memory, each of which holds a single byte. Okay, and their addresses are 00 through FF. Okay, so there, what I want you to kind of think about is excuse me, imagine that you had like the mailboxes that are down in the basement of Sparks, right? That they have numbers on the front of them. So imagine that there's 256 mailboxes and they're arranged in order, starting with 00 and going all the way up to FF. That's a total of 256 of them. Okay? And each mailbox can hold an 8-bit number, and that's it. Okay. Um, Okay, then there are 2 special registers called a program counter and an instruction register, and we'll talk about what those are in a little bit, okay? All right, so let's look at the instruction set architecture, which we started to, I think, last time, okay? But here it is, okay? So we have 12 operations at our disposal on this computer, and there's all 12 of them. Okay, and one of them you could even argue really shouldn't count because the halt instruction that just stopped program execution is not really all that exciting, right? Okay, so there's really only 11 that we'll actually, use a lot. Um, okay, so what are they again? Let's look at the first 3 of them, okay? What do the first 3 do? They allow us to take data from memory and put it into a register, or take data from a register and copy it out to memory. Okay, so data can go either direction, from memory to a register or back. We can copy from one register to another. Okay, the instruction in the book was called move, but it's really copy. So what's the difference between moving and copying, I guess, is like if I move a file from one location to another on my computer, what does that mean? Yeah, exactly. I move it from one place to another, meaning, so how many total copies of the file are there after this is finished? One, okay? Whereas if I copy the file, how many copies are there? 2, okay? So moving on a computer, right? Really what your computer is doing is it's copying and then deleting the original, okay? And that's safer than moving it. And because what happens if like the power goes out halfway through or something? Um, yeah. So copying, right, preserves the source of the data. It just makes a copy someplace else. Okay. So move on this architecture really means copy. Okay. You're copying it from one register to the other, but the original copy, the thing that you started with, is still there. Okay. Now, if you want to get rid of it, you're certainly free to do so. Okay, but it's still there to start with. Okay, then the next block we've got the arithmetic and logical instructions. So we can do addition, and it we can do addition with integers or addition with floats. We can do and, or, and XOR, right? And does that seem like we're missing a few of them? Okay, so like which ones are missing here? Which logical operations? NOR, NAND, right? All of those other ones, okay? Which is actually okay. We can, because we can get all of them by combining the three and, or, and XOR if we're clever, okay? So that's why we don't need separate instructions for all of those. It would be convenient if we had them, but we don't need to. Okay. We've got this thing ROR for rotate right, okay? And that we'll talk about, well, actually, I guess we could talk about it now. So let me take a binary number, okay, and I'm just going to make up something. Okay, so I've just made up an 8-bit number, okay, 10100101. Okay, great. If I rotate this by one position to the right, okay, where is everybody going to go? Well, this one would go to this position. Okay, so you guys agree everybody's moving one spot to the right? Okay, so then the last question then is what happens to that one that's on the far end of the number? It goes to the beginning. Okay, so that's what makes this a rotation, is he comes over here. Okay, now this instruction set doesn't have a version of this called a logical shift. A logical shift would put a 0 here. Okay, so the guy on the far right that fell off the boat would just fall off the boat and he's gone. Okay, but as we'll see in, through the course of our discussion, we can implement a shift by doing a rotate and then doing another operation to change this 1 to a 0. Okay, so maybe here's a good question. Why would we want to shift or rotate bits at all? What's the utility of that? I mean, it's in the instruction set for a reason, right? It's not just there for like, so that means like it ought to be useful somehow. Okay. I guys told you about my my college employment days. Yeah, where did Dr. McKinney work in college? Yeah, he worked at Kohl's. Okay, so let me take another number here. Just I'll make it smaller for the sake of demonstration. Okay, what is that number? 9, right? Okay, let me rotate it one position to the right, and then I'm going to take the one that rotates around and destroy it. We'll talk about how to actually do that later. Okay, so if I rotate all of this one position to the right, I would get this, right? Okay, let me just take that one that came around and replace it with a 0. Okay, what is this number? 4. Okay, so going from 9 to 4, what is that? What have I basically done here? I've basically halved it. Okay, and I say basically because, of course, what's the one minor issue there? Yeah, okay, because this is an integer, so there is no 0.5, right? If we were working with floating point, that'd be another matter, but floating point works differently, as you guys know. Okay, so doing this shifting of one position to the right is like dividing a number by 2, but discarding the remainder. Okay, so think back to when you guys were in elementary school, when you first learned division, right? If I gave you like 24 divided by 7, right, what would you say? Yeah, it was 7, or well, 3 remainder 3, right? Because 7 times 3 is 21, and then there's 3 left over to hit 24. Okay, so you guys would have written the answer as 3 is the quotient and 3 is the remainder. Yeah? Okay, and if you discard the remainder, then you're left with just 3, the quotient. Okay, that's exactly what we've done here, except instead of dividing by 7, we're dividing by 2. Okay, because we're in binary, how many digits are there? 2. It's a base 2 system. Did I tell you guys about the after Christmas sale and the lady with the cart full of stuff? Yeah, okay. So shifting the digits in a base 10 number one position to the right and leaving the decimal point where it is, okay, or equivalently moving the decimal point, right, is the same as division or multiplication by 10, just whichever direction you're going, right? All right, so if we do this in a binary system, shifting one place to the right is like a division by 2. And shifting to the left by one position is like a multiplication by 2. Okay, right, so this is why this rotate command is useful, um, is because it allows us to do shifting if we combine it with another operation. Okay, and yeah, okay. And then the one that's going to make all of this tick, the one that makes this actually a programming, allows us to truly program, is this jump instruction, okay? And the way that's going to work is it will allow us to make an if-then kind of decision, okay? And we'll talk about the mechanics of how it works a little later. But that's the key one here. Okay, so let's go into this, and let's say that I wanted to add the numbers 3 and 5, okay, or whatever, just I'm picking numbers out of thin air. Okay, how would I have to do this? Well, the way I'm going to do this is, let me come down to my examples here, okay? So, all right, instead of 3 and 5, let's do 1 and 2, okay? Only just because that's what I happen to write here, okay? So if I wanted you to add the numbers 1 and 2 on this computer, okay? Up there at the top, we've got the English instructions for how to do it, okay? If everything has to be in a register to be manipulated, or arithmetic done on it, or whatever, right? We first have to get the numbers 1 and 2 into some places where we can do arithmetic with them, okay? So let's take the number 1 and put it into a register. Well, which register? How many do I have to pick from? No, that's the memory. How many registers? There's 256 memory cells, but how many registers are there? 16, okay? For reasons that will become clear later, do not use register 0, okay? You will use it, but for a very specific purpose. And so don't use it unless you are using it for that very specific purpose, and we'll talk about what that purpose is later. Okay, so I'll take the first number, 1, and, well, let's put it somewhere. How about register 1? That seems perfectly logical, right? I could have put it in register F, but I don't, who cares? All right, so I'll put it in register 1. Second, I'll put the other number in register 2. Third, I need to add them, and the answer's got to go someplace. right? The answer's got to go to a register. So what would be a logical place to put the answer? Okay, 3 would be a logical choice. It's not the only choice. Okay, what's the advantage to putting it into 3? Could I have put it back into 1 or 2? The answer? I could have. Why maybe would I not wanted to have done so? Okay, so if I added the numbers and then put the answer back into register 1, what would register 1 now have in it? I'm sorry, I can't. Yeah, the number 3. Okay, what was previously in register 1? The number 1. Okay, so let's say that that number 1 was something I needed to be keeping track of, or I needed to use it later for something else. Well, if I overwrite the register with a different number, what happened to the number 1? It's gone. Okay, so that may be okay, and that may be not okay. Just depends. Okay. Okay. And then I don't have a way to print with this computer. There's no screen or anything. And so in order to sort of output the answer, kind of the convention that I just kind of made up is we'll store it to memory, but we'll store it to the very, very last mailbox. And we'll kind of think of those very last memory boxes as being like a screen, kind of. They're not really a screen, but it's got to go somewhere. Okay. And once we're done with that, we need to halt, right? We finished the program, so halt execution. Is that okay? Okay, so we've written here in essentially plain English, okay, what this, what the instructions are for this program, okay? Do you guys buy it in plain English? Okay, so now we need to translate this from plain English to something that's a little bit closer to actual ones and zeros, but not so close to ones and zeros that it ceases to be human readable. Okay, so we're going to take this down to the level that we call assembly. Okay, and here's what it would look like for this particular program. Okay, so let's kind of look at the pieces here, right? This is mine, right? Okay. You didn't roofie it, did you? Huh? Did you guys hear what he said? He said he's not in a particular fraternity that you guys can guess which one he's referring to. Mm-hmm. Oh, yeah, it's going to take them forever to live that down. So, anyway. Okay, so what's the first instruction that we needed to do? We needed to load the first register, 1, with the number 1. Okay, so the assembly code for that is load 1, comma, 01. All right, so here's the syntax, okay, or how you read this, is the register into which it's going is listed first, and what's going there is listed second. Make sense? Okay. All right. Now, why do I have the hash mark before 01? Okay, this is a convention I made up for this particular computer. Anytime you have a hash mark, it's a specific number, okay, which we could call an immediate number, but it's a specific number. I want to load the number 01, okay? And so anytime I write specific numbers, there's going to be 2 things about them. 1, I will always put a hash mark in front of it, and 2, I will always write the number in hex. But you guys are big boys and girls, so you know how to do things in hex. Although actually maybe last week's exam says otherwise. And where's Cody? Oh, okay. Touche. Yeah. Okay, so great. So I need to load one register with the number 1. I need to do the exact same thing to the other register, but with the other number. Okay, no big deal there. And then you see this stuff off at the right that follows a semicolon. Okay, these are called comments. So in basically any programming language, there's a symbol or symbols or something that you can type, and anything you type after those symbols is ignored by the computer. Okay, and it's only there basically for the human to read. This is where you can put things in English that are notes to yourself or even notes to somebody else. So like if you were on a software development team or something and you had 10 people that were all writing code for some project, well, you better be putting in comments and documenting what you're doing, because some other dude's going to look at your code and be like, huh, right, what the hell's going on here? Okay, so that's what that stuff is. And in the assembly language I made up for this, I use the semicolon to denote that the beginning of a comment. I just, yeah. I should say, by the way, I didn't make all of this up out of thin air. I was looking at other real assembly languages when I did it, because I wanted it to be sort of like a real assembly language, even though it's not the same as any existing one. Okay, so then once I've got the two pieces of data loaded in, what do I need to do then? Yeah, I'm ready to add them. Okay, so let's add them. All right, so here's the syntax for the add command, right? It's add I, because what type of data are we adding here? Yeah, we're adding integers as opposed to floating point numbers. Okay, and so I just put the I on the end there to indicate that it's an integer addition. Okay, and then 3, 1, 2. Okay, what's the order there? 3 represents what? Yeah, that the destination of the answer is going in register 3. Okay, or is register 3. And we picked register 3. It didn't have to be register 3, but that's the one we chose. Okay, and then 1, 2, what does that tell me? The two source registers. Okay, so the destination here in many cases is listed first, not last. Okay, you just have to know the syntax and know which numbers represent what. Okay, then once I've added them together, I want to take the answer, which is sitting in register 3, and copy it out to memory. Okay, and so I chose here to copy it to the very last memory cell, which is cell FF. Okay, I could have picked any other one, but that's the one I chose. Okay, now, so cell FF. Now, what do you notice that's in front of it? Hmm? After the 3, sorry, the $sign. Okay, so here's the other convention I chose. If you're referring to a memory cell, you always put a $sign in front of it. If you're referring to a specific number, you always put a hash mark in front of it. Okay, and what this allows me to do is it allows me to very quickly look at a piece of code and tell the difference between the number FF and the memory address FF. They're not the same thing. Okay, but if I just wrote FF, how would I know that I was talking about memory versus a specific number? I wouldn't. Okay, so hence I put the $sign or the hash mark to indicate which one we're talking about. Okay, is that reasonable? Oui? No. Okay, so we store it out to memory, and then we're finished. We halt the program. Okay? All right, so if we scroll down a little bit, this is still human readable. This is what it is actually in binary. Okay, now what I've done here is on the left, I've put 00020406 and 08. Those are memory addresses, and we'll see why I put them that way in a moment. Okay, but I've done it that way because notice that each line here of my assembly corresponds directly to one of these lines over here down below. Okay, so look at the first two lines of the human readable version and the first two lines of uh, the, the binary stuff down there at the bottom. What do you notice? Yeah. They both begin with 2. Okay, so we have 2101 and 2202. Okay, so could we kind of or reverse engineer what each of the numbers are? So 2101, what does the 2 represent? It represents the load instruction. Okay, what does the 1 represent? The register it's going to. And what does the 01 represent? The number that I'm loading. Okay, does that jive with the next line? It does. Okay, 2202. The first 2 indicates what type of operation we're doing. The second 2 indicates which register it's going to, and the 02 at the back tells me which number. Okay, so I can go from this to this if I know the convention and I know the numbers that go with each operation. Okay, and how do you know those? You know them because my little chart says how they translate to each other. Okay, and just to allay your fears, do you have to memorize this chart? Huh? I don't know. Maybe Cody should have to memorize this chart. What do you guys think? Yeah, you tell him he has to memorize it. Okay, so no, you do not have to memorize this chart. Now, I think you guys will end up kind of memorizing a lot of it by osmosis as we work through this. You know, if you have to look up something 15 times, eventually it's just going to stick in memory. Okay, but no, you do not have to memorize this. So for example, when we get to our final, right, and there'll be questions over this sort of stuff, I will give you a copy of this chart, okay, because I'm a real mensch, okay? Yeah. Okay, but anyway, the chart tells us how to translate from the human readable version to the actual machine version, okay? So just to recap, like what we did an operation number 2 because we were loading a specific register with a specific number, okay? And so what register? I called it R, and then obviously that would be whatever number you type, and then hashtag XY would be whatever number you actually picked. Okay, so my sort of variables here are R, which register number, and what are the numbers X and Y, and this is the order they go in. 2 tells me which kind of operation, R tells me which register, XY tell me what the number is. Okay, is that okay? All right, now, the number 2 that's at the front of this thing is called the opcode because it tells me which kind of operation I'm doing, right? And we have opcodes 0 through C, or sorry, 1 through C, okay? Okay, now let's contrast this, by the way. What's the difference between opcode 1 and opcode 2? They sure look very similar, other than that the number 1 and the number 2 are different. But functionally, what's the difference? Yeah? A specific number, right. So 1 goes out to a particular memory cell to copy the data. The other, you choose the number in advance, okay? Now, in the human readable version, how do you tell the difference between them? It's the difference between a $sign and a hash mark. In the machine readable version, how do you tell the difference between them? What the opcode is, okay? Because the $sign and the hash mark aren't like, they don't mean anything to the computer, right? So yeah, so the opcode is what tells the difference between these two things. Okay, so is that all right? All right, so now let's go back to the code. So what I did was I took this table, right? And I took all of the instructions that I'd written here in human readable form, okay? And then I just translated them into their equivalent machine versions, okay? The first two we've talked about, and you guys can just trust me that 5312, 5 is the integer addition opcode, 3 is the destination register, and 1 and 2 are the source registers, okay? 3 is the opcode for taking things from registers and putting them into memory. Which opcode is, or sorry, which register is the number coming out of? Register 3. And what memory address is it going to? FF, which I just picked arbitrarily. Okay. And then the final operation there, C000, is just the halt command that stops the program from executing. Okay, so next, let's talk about what this number 000204 and so on are. Well, these instructions to be executed have to go out into memory somewhere. Like our computer isn't psychic. They've got to be preloaded into memory. And on this machine, a program must start at the very beginning of memory, okay, in memory cell 00. All right, so what I did is I put my instructions in memory in order, okay? So look up at the top left of the memory compartment. 2101, 2202, 5312, 3F, or 33FF, C000. Does that look familiar? Right, all I did was put the numbers in their appropriate order, okay? And the 000204 and so on just said which memory address starts a particular instruction. The first instruction started in 00, the second in 02, the third in 04, and so on, okay? Those will become important in a moment. Okay, so Gucci? So now let's talk about how this computer actually executes this code, okay? And we're going to do it step by step. There are sort of 3 fundamental steps to execution: fetch, decode, execute, okay? So that cycle will repeat over and over. Fetch an instruction, figure out what the hell it says to do, and then do it, okay? And then you're ready to fetch the next instruction and just continue this. Okay, so the program counter, PC, starts at 00. And what this thing does is it says, which memory cell do I need to go out to get the next instruction? Well, before I've done anything, what should that be? 00, that's where the program starts, okay? And you guys are gonna watch as this program executes, this number is going to count up and go through the memory addresses, okay? The instruction register we'll talk about in just a second. Okay, so let me step, and I'm gonna fetch. Okay, so I just fetched in the 2101. Where is the next instruction that I'd like to load? It starts at memory address 02. Yeah, so that's why my program counter is 02. What's the instruction register now? So IR for instruction register. 2101. Does that look familiar? Yeah, that's our instruction. Okay, so we just fetched it. Well, now what? Well, what the heck does 2101 mean? What does it mean? Load register 1 with the number 1. Okay, oh great. Okay, so we know what we're supposed to actually do here. Okay, and now we have to actually do it. So that's the execute cycle. So if I click the button, notice here, notice what register 1 has in it right now. In fact, all of them have this. What do they all have in them? Yeah, everything's zeroed out, okay? But if I hit step and we go to the next cycle, now look what's in register 1. 1, that makes sense. We just told it to do it. Okay, have we finished executing that first instruction? So now what? We're ready to load in the second instruction and just continue this game. Okay, so I'll step, Well, I just loaded in 2202. That's my next instruction. What does that mean to do? Take the number 2 and put it in register 2. Okay, great. Let's do it. Well, bam, there it is. Okay, step. Well, 5312 is my next instruction. What does that say to do? Add registers 1 and 2 and put the answer in register 3. So I'll do it. And now what's in register 3? 3, the sum. Okay? All right? Well, next instruction, 33FF. What did we say that meant to do? Take what's in register 3 and copy it out to memory cell FF. Yep, that's right. And now, look way down yonder. What's in memory cell FF now? The number 3. Okay, are we finished? Almost. But what's the next instruction? Halt, and executing halt just means it stops executing. Okay, all right, so the step button there will step you through one cycle at a time. Fetch, decode, execute. Individual steps, okay? And that's really useful at first to get a sense for what's going on. Okay, now, if I want to run this quickly, I can hit clear and run, and it will do half a second per cycle, and you can watch a program execute obviously much faster that way. If it's half a second per cycle and it takes 3 of these cycles to execute a given instruction, this thing is running effectively at like 2/3 of a hertz, right? So, because it takes 1.5 seconds per instruction. How fast are the computers that you guys have operate on, their processors? They're fast, much faster, but what? How fast? Come on, guys who have built their own computers. Gigahertz, on the order of several gigahertz. Okay, so we've got something that's operating at basically 1 hertz. That's slow. But it's slow enough that you can watch it happening, okay? Which means you can really then start to understand how it works. And the idea then of this running at, you know, 1,000,000,000 times the speed is, well, okay, it's just really fast, but it's still doing the same crap, okay? All right, have a great weekend. And we're all clear about the retake procedure for the exam you all did so well on. My office, Goodrich 109, okay? Today. Got it? All right. What? Hold on. Let me turn off the stream.